the vision of Tyrannosaurus rex, the ocular machinery of the prehistoric sniper. Imagine a world where the horizon is not a distant boundary, but a detailed map of caloric opportunities. What if the act of observation was so precise that a creature could discern the blink of an eye from the distance of 7 football fields? For this entry into the archive, let us examine the sensory apparatus of the most formidable terrestrial predator to ever walk the earth, Tyrannosaurus rex. Often reduced in the popular consciousness to a lumbering brute with failing eyesight, a victim of Hollywood's movement-based limitations, the reality revealed by the fossil record and biomechanical modeling is far more terrifying and sublime. The tyrant lizard king was not a blind scavenger of the shadows, but a master of the gaze, possessing a visual system that represents the absolute apex of Archosaurian evolution. The archive documents this specimen not merely as a collection of fossilized minerals, but as a living biological computer, designed for the singular purpose of tracking and terminating life with surgical precision. The attribution for this reconstruction rests upon decades of rigorous paleoneurological study and the meticulous analysis of cranial specimens such as FMNH-PR 2081, colloquially known as SU. This archive entry will explore the functional morphology of the tyrannosaurid eye, the evolutionary pressures that sculpted its forward-facing gaze, and the profound ecological consequences of a predator that could see with 13 times the clarity of a modern human. Functional morphology, the anatomy of the orb. The skull of an adult Tyrannosaurus rex was a masterpiece of primordial engineering, a 5-foot-long structure designed to house both a bone-crushing bite and a sophisticated sensory suite. To understand the vision of this creature, one must first look at the vessel that contained it. Unlike many other large theropods, the skull of Tyrannosaurus exhibited a unique narrowing toward the snout, a wasp-waisted rostrum, and a significant widening at the rear. This configuration was not merely for weight reduction or muscle attachment, it was a visceral adaptation to clear the lines of sight for the eyes. The orbits themselves were immense, designed to accommodate eyeballs the size of oranges approximately 13 centimeters in diameter. These are the largest eyes of any known land animal, and their size alone suggests a capacity for light gathering and resolution that defies human experience. In the context of the late Cretaceous, where dense forests and coastal plains provided ample cover for prey, such oversized optical hardware provided a dizzying advantage. The scleral ring and the internal support. In dinosaurs, as in many other vertebrates excluding mammals and crocodilians, the eye was supported by a ring of small overlapping bones known as the scleral ring. This structure served a dual purpose. It maintained the shape of the massive eyeball against the pressures of the surrounding soft tissue, and provided an anchor for the muscles that controlled the focus of the eye. These bones have been found in a variety of theropod fossils, and they offer a proxy for understanding the limits of the animal's visual field. The inner diameter of the scleral ring corresponds to the diameter of the cornea, a measurement essential for calculating the amount of light that could enter the eye. In Tyrannosaurus rex, the size of these rings suggests a pupil that could dilate significantly, allowing for high sensitivity in low light conditions. From the serrated edges of its teeth to the reinforced bone structure of the orbital rim, every part of the T-Rex was built for the hunt. The eye was the commander of this arsenal. Retinal architecture and color perception. While soft tissue like the retina does not fossilize, we can infer its complexity by looking at the closest living relatives of the tyrannosaurs, birds and crocodilians. Modern archosaurs possess a rich variety of photoreceptor cells, including both rods for light sensitivity and cones for color resolution. Because birds are tetrachromatic, meaning they possess 4 types of cone cells, it is highly probable that Tyrannosaurus rex saw the world in an expanded spectrum of color, including ultraviolet light. This ability to see ultraviolet light would have turned the prehistoric forest into a neon landscape of biological signals. Predators with this capability can often track the urine trails of prey, or identify the subtle differences in foliage that might hide a camouflaged herbivore. Imagine the mind-shattering reality of a 6-ton predator that could see the heat of a nesting site or the hidden chemical signatures of a fleeing hadrosaur. It was a sniper that could see through the very fabric of the forest's defense. T-Rex visual adaptations. Eye diameter. Extremely large, 13 centimeters, the size of an orange, allowing for massive light intake. It represents the largest eye of any land animal. Sclerotic ring, a large bony support structure that stabilizes the gaze and enables high-speed focusing. Retinal density, inferred to be highly concentrated, resulting in visual acuity 13 times sharper than that of a human. Pupil shape, round, standard for high-level predators, allowing for consistent focus across a wide range of distances. Nictitating membrane, an inferred translucent third eyelid that kept the eye moist and offered protection during combat. The Kent-Stevens revolution, binocularity and depth. The most dramatic advantage of Tyrannosaurid vision was not its size, but its orientation. In most vertebrates, the eyes are placed laterally, providing a panoramic view of the world at the expense of depth perception. This is the vision of the prey, a constant, flat scan of the horizon for movement. However, the eyes of Tyrannosaurus rex were rotated forward, creating a significant overlap in the fields of view of the left and right eyes. The work of Kent-Stevens using the Dinomorph project transformed our understanding of this orientation. By employing inverse perimetry, a technique where light is projected outward from the orbits of scale model skulls, Stevens mapped the binocular field of view of various theropods. The results were poignant. While an Allosaurus possessed a binocular overlap of only 20 degrees, Tyrannosaurus rex exhibited a BFOV of 55 degrees. The geometry of the kill. A binocular range of 55 degrees is superior to that of a modern hawk, an animal synonymous with aerial precision. This overlap allowed for stereopsis, the ability of the brain to calculate the distance to an object based on the slight differences in the images received by each eye. For a massive predator navigating a complex environment, this depth perception was not a luxury, it was a mechanical necessity. A Tyrannosaurus had to judge the exact distance to a Triceratops' flank to deliver a killing blow while avoiding the lethal sweep of its horns. The wider the separation between the eyes, the more effective this depth perception becomes at greater distances, a phenomenon known as binocular parallax. Given the massive width of the Tyrannosaur's skull, its ability to see in depth likely extended for kilometers. The Tyrant King did not just see its prey, it mapped the prey's position in three-dimensional space with the cold accuracy of a surveyor's tool. Visual acuity, the sniper's resolution. Visual acuity is the capacity to distinguish fine detail. It is the metric that separates the observer from the sniper. Stevens' research concluded that Tyrannosaurus rex possessed a visual acuity approximately 13 times that of a human. This means that an object a human could clearly identify at 1.6 kilometers would be visible to a Tyrannosaurus with the same clarity at a staggering 6 kilometers. This level of precision is achieved through a combination of eye size and foveal density. In modern reptilian birds, a specialized region of the retina called the fovea acts as a biological telephoto lens. While we cannot examine the fovea of a T. rex, the mechanical constraints of its large eyeball, which projected a massive image onto the retina, ensure that its resolution was among the highest in the history of terrestrial life. Visual capability comparison. Superior long-range vision. The Tyrannosaurus rex dominates in clarity, boasting visual acuity 13 times higher than a human and a maximum clarity distance of to 6 kilometers, significantly outperforming the bald eagle to 3 kilometers. Binocular overlap. While humans, 120 degrees, and domestic cats, 130 degrees, have much wider binocular overlap, the T. rex 55 degrees still surpasses the bald eagle, 340 degrees, and the Allosaurus 20 degrees, indicating better depth perception than other predators listed. Allosaurus limitations. The Allosaurus is shown to have the weakest visual stats, with a narrow 20 degrees overlap and unknown likely low acuity. Neurobiology, the sensory command center. The vision of the Tyrannosaurus did not exist in isolation. It was integrated into a neurobiological hierarchy that defined the creature's existence. CT scans of brain cases, particularly the exceptionally preserved specimen Sue, reveal a brain that was massive and highly specialized. While the olfactory bulbs were indeed gargantuan, indicating a sense of smell that could detect a carcass from miles away, the optic lobes were equally well developed for a dinosaur of its size. The encephalization quotient, EQ, of Tyrannosaurus has been estimated at 2 to 2.4, suggesting a level of intelligence comparable to a modern primate or a social carnivore like an orca. This intelligence was the ghost in the machine that processed the massive influx of visual and olfactory data. A Tyrannosaurus did not simply react to movement, it calculated, patterned, and anticipated. Gaze stabilization and the flocculus. A critical feature of the Tyrannosaur brain was the enlarged flocculus, a part of the cerebellum responsible for stabilizing the gaze during movement. In a predator that weighs 8 tons and moves with the momentum of a locomotive, maintaining a steady image of the target is a daunting biomechanical challenge. The flocculus coordinated the movement of the neck and eyes, ensuring that even as the T-Rex charged through uneven terrain, its focus remained locked onto its prey. This stabilization suggests that Tyrannosaurus was an active pursuer rather than a sluggish scavenger. It possessed the vestibular and optical hardware of a creature built for high-stakes, high-speed interaction. The Tyrant King moved through its world with a stabilized, high-definition feed of its environment. It was a visceral synchronization of muscle and mind, the synergy of sight and scent. There is a long-standing debate regarding whether Tyrannosaurus was primarily a predator or a scavenger. The sensory evidence suggests the question itself may be a false dichotomy. Its massive olfactory bulbs were suited for tracking carrion over vast distances, similar to a turkey vulture. However, its high-acuity binocular vision is a hallmark of an apex predator. The most likely reality is a sensory synergy. The nose found the general vicinity of the food, and the eyes conducted the final, lethal reconnaissance. In the low light of dawn or the dense shadows of a coastal forest, the T-Rex used its nose to narrow the search and its sniper vision to pinpoint the target. It was a predator that used its senses in layers, each one refining the work of the last. Evolutionary context: the sculpting of the king. The visual prowess of Tyrannosaurus rex was the result of a multi-million-year evolutionary trajectory. Early tyrannosauroids, such as the Jurassic Stogosaurus or the early Cretaceous Delong, were much smaller and possessed more laterally oriented eyes. As the lineage increased in body size, the sensory systems underwent a radical transformation to support the demands of an apex niche. From panoramic to focused. The transition from a panoramic view to a binocular gaze represents a fundamental shift in ecological philosophy. In the mid-Cretaceous, as tyrannosauroids began to replace the allosauroids as dominant predators, their skulls began to widen at the back and narrow at the snout. This snout narrowing was a selective advantage that improved the binocular range by removing the physical obstruction of the rostrum. 1. Visual superiority of T-Rex, comparative data. The first table compares the Tyrannosaurus rex to other species, highlighting its exceptional eyesight. Unmatched clarity. The T-Rex possesses the highest visual acuity, 13x better than a human, and the longest range of clarity to 6 kilometers, significantly outperforming the bald eagle. Binocular vision. With a 55 degrees binocular overlap, the T-Rex has better depth perception than the Allosaurus 20 degrees and bald eagle, though it is narrower than the modern human 120 degrees or domestic cat 130 degrees. 2. Evolutionary progression, evolutionary stages. The second table illustrates how tyrannosaurid vision evolved over time to support their changing ecological roles. Basal stage. Early ancestors were small generalist predators with primarily lateral vision, side-facing eyes. Intermediate stage. As they became large specialized hunters, emerging binocularity began to appear. Apex stage. Rex. The final evolutionary form features advanced binocularity, a crucial adaptation for a top-tier apex predator to judge distance and hunt effectively. This progression was likely driven by an arms race with their prey. As herbivores like ceratopsians and hadrosaurs developed more sophisticated defenses and herd behaviors, the predators that survived were those that could identify weaknesses from a distance and strike with precision. The vision of the T-Rex was not an accident. It was a requirement for its reign. The limits of movement-based vision. The myth that Tyrannosaurus could only see moving objects is a fascinating case of scientific fiction bleeding into public perception. This idea was based on a misunderstanding of certain reptilian visual systems, where neurons in the optic tectum respond preferentially to motion. However, an animal with a 5.5-degree binocular overlap and 13x human acuity would have no difficulty distinguishing a stationary human from a tree. In fact, binocular vision is specifically designed to break camouflage. By seeing an object from two different angles, the brain can see around the leaves and shadows that might hide a motionless animal. To stand still in front of a Tyrannosaurus rex would not be an act of survival. It would be a tragedy of misunderstanding. The Tyrant King saw the world in high-definition stillness. Ecological impact. The reign of the gaze. The presence of a predator with 6-kilometer vision fundamentally altered the ecology of the late Cretaceous. This created what ecologists call an ecology of fear, where the mere possibility of being observed by the apex predator dictates the behavior of every other organism in the environment. The sniper in the forest. The Tyrannosaurus likely employed a strategy of pursuit predation mixed with ambush. Using its superior sight, it could monitor the movements of herds from a distance, identifying the young, the old, or the injured, without ever revealing its own position. Once a target was selected, the T-Rex could use the terrain hills, riverbanks, or dense stands of redwoods to close the distance. The sniper analogy holds true in how the T-Rex used information. It did not need to be the fastest animal in the ecosystem. It only needed to be the most informed. By the time a hadrosaur realized it was being hunted, the Tyrannosaurus had already calculated the distance, the path of intercept, and the most efficient point of attack. It was a predator that killed with information as much as with teeth. Nocturnal dominance in the vitamin A race. The possibility of nocturnal hunting adds a layer of grotesque horror to the T-Rex's ecological role. As previously noted, the large eyes and potential for a tapetum lucidum suggest that the Tyrant King was comfortable in the dark. This would have given it a profound advantage over herbivores, whose plant-based diet was deficient in vitamin A, the chemical precursor for rhodopsin, the pigment required for night vision. While the T-Rex had a constant supply of vitamin A from the livers of its prey, the herbivores were biochemically limited in their ability to see at night. This created a nocturnal window where the Tyrannosaurus was effectively a god of the shadows, hunting creatures that were functionally blind. The night was not a time of rest for the Cretaceous world. It was the time when the sniper truly ruled. Case study: the specimen Sue in visual pathologies. The specimen FMNHPR 2081, or Sue, offers a poignant look at the life of a visual predator. Sue was a geriatric Tyrannosaurus, living to the age of approximately 28 or 33 years, a record for the species. Her bones tell a story of a hard, violent life. Broken ribs, a torn tendon in the arm, and a massive infection in the leg. Parasitic infection and sensory loss. Most intriguing are the round holes in Sue's lower jaw, once thought to be bite marks, but now identified as the result of a Trichomonas gallinae infection, a protozoan parasite that infests modern birds. In birds, this infection causes severe swelling of the throat and can eventually lead to starvation. For a predator that relies on high-speed bites and a precise sensory motor loop, such an infection would have been agonizing. Furthermore, any infection that affects the cranial region has the potential to impact the optic nerves or the vestibular system. As Sue aged and her body succumbed to arthritis and parasites, her world may have slowly blurred. There is a tragic irony in the idea of the world's most acute visual predator slowly losing its ability to see the world it once ruled. In her final years, Sue may have been a broken sniper, relying on her still potent sense of smell to find food she could no longer see with clarity. The optics of predation, a biomechanical analysis. To truly appreciate the sniper vision of the T-Rex, one must look at the mathematical limits of its eyes. The blur circle diameter in the eye of a predator determines the depth of field and the clarity of the image. For a vertical slit pupil, the blur is proportional to the aperture diameter, and the difference in diopters between the eye's focal distance and the point of interest. Using the small angle approximation, we can estimate the blur circle diameter beta in radians as beta equals A times delta D, where A is the diameter of the pupillary aperture and delta D is the difference in diopters. For a Tyrannosaurus rex with an orange-sized eye, even a small pupil would provide a massive aperture compared to a human. This means that while its depth of field might have been narrower than a cat's, the absolute resolution of its in-focus zone was mind-shattering. Gaze stabilization and the senses. The biomechanical stabilization of the eye is also critical. The formula for the angular resolution theta of an eye is given by theta is approximately equal to 1.22 lambda over d, where lambda is the wavelength of light and d is the diameter of the pupil. With a pupillary diameter many times larger than a human's, the theoretical resolution limit of the T-Rex was incredibly small, allowing it to distinguish two objects as separate even at vast distances. This is why the 6-kilometer figure is not just a guess, it is an optical inevitability of having such large hardware. The philosophical mirror, the charisma of the tyrant. The Tyrannosaurus rex is more than a biological specimen. It is what some scholars call a disruptive object in the human desirescape. The fascination we feel when looking into the empty orbits of a T-Rex skull is a mixture of terror and kinship. We are both predators, and we both define our world through our gaze. The price of the gaze. The discovery of specimens like Sue and Stan has led to million-dollar auctions and intense legal battles. In 1997, Sue was sold for $8.3 million. In 2020, Stan was auctioned for over $31 million. This financial desire is a testament to the charisma of the T-Rex, a quality that stems directly from its status as the ultimate super predator. We value these fossils because they represent a peak of existence that we can scarcely imagine. Yet, there is a war of nature underlying this beauty. Darwin spoke of the grandeur in this view of life, where from the struggle for existence, the most exalted object is produced. The vision of the T-Rex was the crowning achievement of this struggle. It was a tool perfected by millions of years of death, a visceral testament to the efficiency of evolution. The humanistic reflection. As we conclude this entry into the archive, let us reflect on the nature of perception. To have the greatest eyesight of any animal on land is to live in a world of absolute clarity, where every detail of the environment is a signal for survival. But that clarity did not save the Tyrannosaurus. The asteroid that ended the Cretaceous did not care for binocular overlap or 13x visual acuity. The Tyrant King, who could see a hadrosaur from 6 kilometers away, could not see the end of its own world. There is a poignant tragedy in the fossilized eye. It reminds us that all our senses, no matter how advanced, are calibrated for a specific time and place. The T-Rex was a masterpiece of its era, a sniper whose world was a perfect alignment of optics and intent. Today, its eyes are hollow, and its gaze is a memory. We look at it and see a reflection of our own fragile dominance, a reminder that the most exalted objects of nature are but fleeting moments in the archive of time.